It's now my pleasure to announce the last speaker of the session. Ludovic Righetti is an associate professor at New York University. He also is an international chair at the Artificial and Natural Intelligence Toulouse Institute. He's also vice president of MAP, Media Services Board. He was at the University of Southern California and also the Max Planck Institute before, and also got a number of awards, again the George Giralt PhD Award, RAS Early Career Award, and also the Heinz Meyer Leibniz Prize. And he will be talking about the long and winding road of optimization for legged locomotion. The floor is yours, Ludovic.
All right, thank you, Katja, and hi everyone. Thanks for being here. Today I'd like to talk to you about the optimization for leg robots. So I'm very much interested in algorithms in general. And a year ago, this is the result that we published at ICRA. So this is work I did in collaboration with the team of Nicolas Mansart at the last CNRS in Toulouse, France. And you can see a quadruped that is using a single policy to cross various terrains, right? So we use reinforcement learning to optimize that. So we optimized one single policy that was able to generate all the behaviors that you see. And we use vision in the training, so the robot can use the cameras to detect the obstacles and decide what it needs to do based on the type of things that it sees. A side thing, we're not using any behavioral cloning, so it's really trained, everything is trained using purely reinforcement learning. And if you would have asked me 5 years ago, I would have told you that something like that probably will never work, right? I would say that you will not be able to do that with just reinforcement learning. And obviously I was wrong. So one of the questions is that what has happened, right? And is reinforcement learning really kind of a paradigm shift in locomotion? So before we go into that, I would like to define what we're really talking about. So reinforcement learning, right, is the problem. You try to solve an optimal control problem, which say you want to minimize some performance cost, or you want to maximize some reward, which is the same thing, right, over some time horizon n. And so you want to find the controls that will minimize this cost over n time steps. And usually what you do is that you have a simulator when you can simulate thousands of robots that do various things, and then you use the results of this simulator to optimize the policy pi, which is going to map your sensors or your state of your robot into a control action, right? So for every possible state that you have, you will have an associated control action that is supposed to be the best thing that you can do to solve your problem. So what is quite conceptually interesting is that here what we're optimizing is actually an infinite dimensional object, right, which is a function that will map every possible state to an optimal action. And because this is a very difficult problem and very large problem to solve, right, usually this is done offline. So when you do reinforcement learning, you do offline optimization, and when you're done, you take your neural network and you evaluate it online. But there's no more reasoning going on once you've done that. The paradigm that is kind of concurrent to that is model predictive control, which is a very different conceptually. So you try to solve the exact same problem, right, which is an optimal control problem, but you try to do it online. Because you try to do it online, you cannot optimize a function, right? You can only optimize a trajectory. So you measure your current state, and then you compute what is the best thing that you can do to solve your problem given your current state. Then you execute what you computed, and you measured your next state. And obviously, the environment has changed, so now your optimal solution has changed, and you recompute it. So basically, you keep doing that forever, so you need to solve an optimization problem, but online. So now you can see the problem, because now we have a very strong computational requirements to be able to do that at very high rate. So now we are solving a finite dimensional problem here, which is finding a trajectory. But we need to do it in real time. So that's the big thing. So these two things are really solving the same problem. So now one of the questions is that is RL a paradigm shift for locomotion? And I think you can say yes, because with this kind of techniques, we're able to generate complex behaviors we are not able to generate before, right? And we saw in the talk before, right, that you can do things for leg robots that it's very difficult to do with just model predictive control. One of the greatest things, I think, is that we can integrate multimodal sensing, for example, vision, and which is a really big deal. And we also can deal with discontinuous dynamics. So we can use models that are very complicated, like full simulators, which is really hard to do if you use other optimization techniques. And this is due to the fact that the way we sample things in RL has some smoothing effect that makes actually learning possible. And maybe the last thing that is probably the most important part of that is that it's actually really easy to use. In order to use reinforcement learning, you don't need to know anything about numerical optimization. You don't even need to know how the algorithm works. You can literally, the community has developed very good packages. You can just use them, and you're going to be able to get your robot to work. On the other side, you could say, well, it is nothing new, right? Because it's just solving optimal control problems that the community in leg locomotion have been trying to do for 30 years now. Another caveat here is that everything that you've trained offline, it's frozen. So there's no more online reasoning when you do that, which means that if anything happens outside of your out of distribution, this is not going to work anymore. You're usually bound to local minimum, right? We're really good at doing RL for locomotion, but to do that for manipulation is very difficult. And maybe the last point for people who really care about algorithms is that RL algorithms are not very efficient, right? They take a lot of time to optimize things. So if you want to put this kind of algorithm on a graph, when you look at the complexity of the models that we're using to do the optimization, right, for very simple linear models to full simulators, and how much time it takes you, so whether you can do these things online or if you have to do this offline before deployment. Model-free RL, right, will be there. You can use the most complex simulators that you have, but it might take you hours to compute a solution. Which is really interesting because if you think about it, 20 years ago, I think there was another kind of paradigm shift that happened in leg locomotion, which tried to do the complete opposite. So the idea is, say, how can I solve, with very simple models, solve an optimization problem, but in real time as fast as possible, right? And that was really the advent of understanding that you can use real-time optimization in the control loop. And this work of Kajita and Weber that really understood that you can write, so you can simplify the dynamics of your robot using a linear pendulum model, and then you can solve online quadratic programs that will give you the optimal behavior for center of mass trajectory. And this was kind of a big deal at the time, right? Because then you could do things like that. So this is the work of Olivier Stas that implemented some of the controllers from Weber and his colleagues. And you have a locomotion, right, of HRP2 walking around. You can control its direction. This is all generated on the fly, right, as we go. And this has really spurred a lot of research in these things. So even in my lab, 10 years later, we're still looking into these same models to do. So here we were doing more dynamic walking, right, because we changed a little bit how we think about the problem. But conceptually, it's really these ideas, right? This idea that you want to do optimization online, and you want to do it as fast as possible. So once you can do that with linear models, the next question is, why don't I use full complicated models that are really difficult? Because then I can do more than just walking on flat ground. I can actually do arbitrary behaviors in principle, right? So that's where you want to go. The problem is that if you use just a solver that you find online, right, optimizers that just exist, this is where you want to go, right? It's going to take you hours to solve a problem. So the community has spent a lot of time designing solvers that are really fast, that can be run in real time. So in my lab, we spend a lot of time designing solvers like that. So you can see examples now on running nonlinear MPC with constraints on various robots. You saw the robot doing dynamic movements on the right. And here on the left, it's a full force control robot with force feedback, where here we add arbitrary constraints on the fly, and we add disturbances, and we solve the problem at the kilohertz, right? So we solve the optimization problem 1,000 times a second, and you can get this very nice behavior that is really, really hard to do otherwise, right? And this is probably one of the fastest solvers that exist today, right? So we compare this with existing solvers. In blue, this is our solver, so it's really, really fast. And one of the things that we realized, it's kind of a disappointment, is that the actual algorithm that we implemented is nothing really new. So we really implemented textbook ideas, but with modern numerical methods to do that. So one key insight that I learned this past 10 years is that don't reinvent the wheel. People who actually do optimization are much smarter than me, so we should read their papers, and usually this is how you get really good results. So this resonates, right? Because as a community, we went from there to being able to do nonlinear MPC in milliseconds on real robot. So the next thing we looked at is, can we actually speed up also model-free reinforcement learning? Can we speed up reinforcement learning, right? And one of the most recent work we've been doing is say, well, let's think about not just sampling PPO style and doing some policy update, but let's try to see if we can optimize with gradients, because we're going to get much faster convergence. So instead of doing just pure model-based reinforcement learning, what we did is try to use the full simulator as a way to generate trajectories. So that's what we call the forward pass. And then along those trajectories, what we do is that we learn a model, but not the model of the dynamics. We learn a model that is going to be smoother, learn a model that we will use only to compute gradients. So then you get the full simulator to generate your dynamics, to your behavior, and you learn a model of the gradients that you're going to use to do gradient descent. And if you combine these two things together, this works really well. So this is an example of a policy you can optimize with that, of the robot balancing on 2 legs. And in blue, so you have 2 graphs that show you the sample complexity and the time complexity. In blue, this is our method. And in green, you have PPO, for example, and we see you have orders of magnitude faster in terms of more sample efficient. And we are about two times faster in terms of time efficiency by doing that. So you really gain a lot by really looking at how the optimizer can be designed in a smart way, right? So the next thing you could ask, say, why don't you do both, right? Why don't you do online reasoning and offline pre-processing? So I think it's very interesting, and there's a lot of things you can do there, and I just want to show you one thing, because I think it carries interesting things. We did some work when you try to learn a value function, and then you use model predictive control plus the value function in your cost, such that you can get this infinite horizon behavior. Because if you do model predictive control, usually you have a very short horizon, so you tend to get stuck in local minimums. But if you have an infinite horizon thanks to the value function, then you don't get stuck in this local minimum anymore. And then you can say, well, why don't you just learn a policy? Why do you care about doing things online? So if you only learn a policy, this is the kind of cost that you get. So you get very reasonably good performance, but you're not very precise. But then if you combine the learning with the online refinement of your behavior, right, dealing with constraints and things like that, you get almost 2 orders of magnitude better performance. You get much more precise into your behavior. In addition to that, if you're out of distribution, it doesn't matter, because your optimizer online is going to take care of the constraints and all the things you've never trained for offline, right? So there's a lot of promise in really combining these 2 things together. So the next step, now we have full simulators. We want to have more complicated simulators. We want to have also models that are learned directly from real robot data that are maybe world models. And the next thing is going to say, how are we going to combine this offline and online reasoning with much more advanced models and more complicated models that we cannot really take derivatives of anymore and things like that. So I think this is really exciting in that point of view. And maybe my last thing I would like to talk, so far I've only talked about algorithms, and I kind of made the claim that by building smart algorithms, you can really, leg locomotion was really advanced by smart algorithms. And I think it's not completely true. I think maybe the biggest paradigm shift that we've seen in our field is the fact that robots are accessible to everyone today. So when I started my career, you can only had robots. Either you build them, so it would take you years to build a robot, or you part of a big company that has really cool robots that they don't want to share with anyone, right? But today, you have great hardware that you can get, and you can get at a not crazy price. We also have amazing learning frameworks that are very easy to use, right? We have really good simulators, and we start to have really mature optimization algorithm we can use online. And I think really, maybe more than just the algorithmic or scientific part, the fact that things are accessible means that a lot of people can do that, and the time from ideas to experiments have already decreased. So I think as a community, that's maybe one of the biggest wins we had these past years, is to have a much larger community than before. On that note, thank you so much for listening to me, and I'm happy to answer any questions.
Okay, thank you very much, Ludovic, for these great insights. Are there questions? If yes, please step up quickly to the microphone. Is that okay? It's hard to, you again. Otherwise, I also have one.
I'll just ask a question. I really liked your talk, Ludovic. I think the idea of bridging the MPC and RL worlds is nice. I guess my only real question is, are you basically sacrificing in terms of computation, right? Where you now have you show great timing, time to compute, but I guess we're all a little bit maybe concerned about resources and electricity use, server use, all that stuff. So I'm just curious about that point, if there's any compromises here. Maybe this is a stupid question, but
No, I'm not sure. I didn't understand correctly. You're asking about computational efficiency of the algorithm and whether we need to make this better or not?
Yeah.
Okay, yeah.
Yes, sir.
So actually, yeah, there is, right? So I think it's really, first, if you want to really train these things at scale, and we really care a little bit about the, energy consumption, we really need to have much better algorithms, right? We cannot just be so wasteful, but that's one thing. The other thing, right, why not synthesize policies on the fly? Right? We are not able to do that today, but it would be really amazing if I could synthesize policies on the fly, and we limited hardware. So there's a value to designing much better algorithms that are much smarter in what they do. There's another thing is that we're starting to get much more interesting models that can, simulate soft bodies, soft materials, and things like that. You want to train things with real robot data as well. With the algorithms that we have, either RL and optimizers, they cannot deal with that yet. So we really need to think hard about the algorithmics. And I think just learning from demonstration, for example, you don't have the reasoning aspect. So online reasoning, dealing with very complicated models, really call for smart algorithms. I think it's really exciting. I don't know yet how we're going to do that.
Yeah, really interesting. Thank you.
Okay, yeah, I also have more questions, but I think we have to come to an end because I already see the next session waiting. So thank you very much again. And also thanks to all speakers. Yeah.